Hello everyone, my name is Yue Wu from Computer Science Department of Yale University. Today I'm going to talk about our recent work on quantum error correction. I will first talk about our findings about the interpretation of the unified decoder on weighted graphs, and then I will show an application of that interpretation on the XZZX surface code. Minimum weight perfect matching decoder, or MWPM decoder, is a popular decoder for surface code with high accuracy and relatively low time complexity. Several works have shown that the unified decoder has similar threshold with MWPM decoder, and more interestingly, they can use the same weighted decoding graph. This is uncommon because the unified decoder was proposed in a way that has nothing to do with minimum weight perfect matching. So one would ask, what is the underlying relationship between them? And also, under what conditions unified decoder has the exact same accuracy with MWPM decoder? Let's first quickly recap the surface code. This is a single logical qubit with code distance of 3. It consists of several data qubits, and there are several Z stabilizers that can detect X errors on the adjacent data qubits. Similarly, there are some X stabilizers detecting Z errors on the data qubits. Now we only focus on the Z stabilizers and try to correct those poly X errors. And of course, the same procedure is applied to X stabilizers as well. We next look at the bigger code patch with code distance of 11. We convert those data qubits into dotted lines that connects the stabilizers which could detect errors on them. Data qubits on the left side and right side is only stabilized by a single Z stabilizer, and so we convert them into a so-called virtual boundaries. After measuring those stabilizers, some of them will give non-trivial measurements, and hopefully most of the measurements are trivial, and we will just hide them and focus on decoding those non-trivial ones. Looking at this example of non-trivial measurements, there are multiple error patterns that could produce it. The task of a MWPM decoder is to find the most likely one. In this example, the one on the left is more likely. On the other hand, if a decoder failed to do so, for example, if the real errors are on the left, but the decoder gives a correction pattern on the right, a logical X error would occur after applying the correction. A logical error is basically an error chain connecting the left and the right boundaries. Let's then look at how unified decoder works. All non-trivial measurements are considered odd clusters at first and starts expanding their exploratory regions. When clusters touch each other, they merge into a bigger cluster. In this case, the bigger cluster is still an odd cluster consisting of 3 vertices. When clusters merge into an even cluster, they will stop expanding. When the odd cluster touches an even cluster, it becomes a huge odd cluster and keep expanding. Finally, when it touches either the left boundary or the right boundary, it will stop expanding. After all the clusters stop expanding, unified decoder will apply peeling algorithm. It finds an error pattern that cancels out all the non-trivial measurements, or the syndrome, using only errors inside each cluster. And it turns out that this error pattern corresponds to a perfect matching, although usually not minimum weight perfect matching. We then look at how MWPM decoder works, which uses the Blossom algorithm as a MWPM solver. Here we will have to dig into the Blossom algorithm in order to find the similarities between the unified decoder and MWPM decoder. There are some internal variables called dual variables during the execution of the Blossom algorithm. We will visualize these dual variables in this diagram as the radius or width of the exploratory regions. For people who are familiar with the Blossom algorithm, the concrete values of the dual variables are placed on the left. Otherwise, don't focus on those numbers because we are not going to talk about them in details in this talk. At first, it seems pretty like the unified decoder that all vertices are expanding. Different things happen when they merge together. In the Blossom algorithm, vertices ABC forms a so-called blossom. Individual vertices A, B, and C stops expanding, but this blossom will start expanding. When vertices D and E touch each other, they will stop expanding and form a temporary match. Later on, the blossom touches this temporary match and forms an alternating tree. This is especially different from what's happening in the unified decoder. When updating an alternating tree, it will expand some exploratory regions as usual, but it will also shrink some others. In this case, D is shrinking. This alternating tree then forms a huge blossom. Eventually, this blossom touches the left boundary and terminates. The blossom algorithm returns a minimum weight perfect matching. It will only match vertices inside each cluster. If we can use the concept cluster here as well. After taking the result from the blossom algorithm, MWPM decoder will generate an error pattern corresponding to this perfect matching. Let's compare these two decoders. They both find a perfect matching, but only MWPM decoder finds a minimum weight perfect matching. If we use the same language to describe both of them, that is, all errors are inside clusters. Let's look at them in parallel again about how they evolve. You may notice that the shape of their clusters look pretty similar. If we combine them together, the bottom dark region is the difference between their shapes. In this example, the correction patterns of the unifying decoder and MWPM decoder only differ by several stabilizer operators. It turns out that because of the degeneracy of quantum codes, even if unifying decoder doesn't find the most likely error pattern, it decodes this syndrome as good as a MWPM decoder. Now, we can answer the questions at the beginning. By knowing how these two decoders evolve similarly, we come to a conclusion that the unifying decoder is an approximate MWPM decoder using the same weighted graph. Unifying decoder drops all the internal details of clusters, while the blossom algorithm keeps them. Unifying decoder and MWPM decoder each has its strength and weakness. Inspired by this interpretation of the unifying decoder, maybe we could combine the unifying decoder and the MWPM decoder together so that it can balance between decoding time and accuracy. For example, by dropping internal details of clusters only when it's too large. We can also answer the second question now by giving some conditions of when they will have the same accuracy. The first condition is all clusters have the same shape in unifying decoder and one possible solution of the blossom algorithm. Why I'm saying one possible solution here is because the shape of exploratory regions in the blossom algorithm is not unique. Here are three possible shapes when the blossom algorithm terminates. As long as the unifying decoder has the same shape as one of them, it satisfies this first condition. The second condition is about corner cases, where a cluster touches both the left and the right boundaries. When this happens, unifying decoder is always confused. However, in some extreme cases, MWPM decoder can still identify the unique most likely error pattern. So the second condition requires that when it happens, the syndrome must inherently confuses both the unifying decoder and MWPM decoder. If these two conditions are satisfied, then unifying decoder is equally accurate as MWPM decoder. Next, we will look at an application of this interpretation. It turns out that in XZZX surface code with infinite noise bias under perfect measurements, both the two conditions stand. First, the shape of them is always the same as shown in this example. The second condition is also true for any code distance. This means that unifying decoder should be equally accurate as MWPM decoder in this case. Using numerical simulations, we confirm that analytical result. We are fixing the physical error rate to 7% here and changing the noise bias eta. Unifying decoder is indeed equally accurate as MWPM decoder when the noise bias goes to infinity. You can see the accuracy loss of the unifying decoder vanishes when the noise bias goes high. We then consider the more realistic circuit-level noise model. In this case, analytically, they are not expected to be equally accurate because the conditions don't stand. Numerical simulations show that under a high noise bias of 100, the unifying decoder reached a 0.9% threshold, lower but very close to the 0.98% threshold of the MWPM decoder. A single takeaway sentence from this talk would be, the unifying decoder is an approximate MWPM decoder. One of our future works is to incorporate the unifying decoder and MWPM decoder for a more flexible decoder so that one can trade off between the accuracy and decoding time.